Okay, so another reason we use Dalton's law of partial pressures is to account for water vapor within a system. Water vapor may be present in a sample because commonly when we're collecting gases in a reaction, we're using the displacement method. So we didn't actually do this referenced acetylene combustion lab, but this is one that I showed you the results of in the test tube that showed incomplete versus complete combustion. So basically what you're doing is you're holding a test tube inverted that's full of water over another reaction vessel that has water in it. As the gas bubbles up from the reaction, you're collecting it in the top of that test tube and the water is getting pushed down through the test tube. So because you are collecting it over water, your gas tends to be saturated with a little bit of water vapor as well. So the amount of water vapor present varies with temperature within your system. So if you flip over your periodic tables to your water vapor pressure table here, you'll see that we're looking at the temperature in degrees Celsius compared to the amount of pressure exerted from that water here. So let's just look at those units. Hopefully you can also see here that as the temperature increases, the amount of pressure exerted on the system from water also increases. And this is because as the temperature is increasing, you're getting closer to that evaporation point. So remember, water is going to go from liquid to a gas at 100 degrees Celsius over here. And so at that point, all of the pressure exerted on the system is coming from water because that water should be evaporated, so it's purely just hanging out as a gas. Now it's no longer hanging out in liquid form. Okay, so how can we use this table in a question? So let's look at the example number 4 that's written here. So a quantity of gas is collected over water at 8 degrees Celsius at a pressure of 84.5 kilopascals. I made a mistake in this question. Can you also add in, please, that the volume is 353 centimeters cubed? What volume would the dry gas occupy at standard atmospheric pressure at 8 degrees Celsius? So a hint here that I need to use the displacement method to collect is that it's asking for the dry gas, which means that I need to take out the amount of pressure exerted from the water before I can do my calculations. So just like we've done from all of our other gas law problems, the first thing that I need to do is outline all of my variables. So P1, V1, and T1, as well as my final conditions, P2, V2, and T2. Okay, so in the question it says a standard atmospheric pressure. So because P1 is written in terms of kilopascals, P2 also must be kilopascals. So my standard pressure would be 101.3 kilopascals. And hopefully these values are starting to cement themselves in your brain. So if I look at this, initially I would probably think, well, shoot, my temperature is in degrees Celsius, so I need to convert that into Kelvin. However, if I look at these two temperature values, notice that they're the same, or I could say that they are constant to each other, which means, whoa, that's funny, which means that I don't really need to take those into account when looking at my calculations because they're just going to cancel each other out. If I converted them to Kelvin, I put it into the combined gas law, sure, it'll all work because it'll all just cancel out in the end, but that's more work for you. So instead, what I'm going to use that temperature for is to account for the amount of water pressure in my system. So let's go back over to that water pressure chart, and we're dealing with 8 degrees Celsius. So on your water pressure chart, you need to find 8 degrees Celsius, and that's exerting 1.1 kilopascals of pressure on the system. So remember we said that P total equals P1 plus P2. If I'm saying that P1 is the gas that I care about, maybe P2 is my water pressure that's hanging out there. So if I substituted my values, I know that the total pressure of my system is 84.5 kilopascals. P1 is what I'm trying to find, and P2 would be this 1.1, remember the pressure exerted from the water. So if I'm trying to solve for this value here, my P1 pressure, then all that I'm doing is subtracting 1.1 from 84.5. So let's do that over here. So minus 1.1, and that would give us 83.4. Okay, so now I have all that together. Remember, I don't need to account for the temperature because it's constant. So really all that I'm doing here is using Boyle's law. So P1 V1 equals P2 V2, and now I can plug in all of my values. So remember, we're using our dry gas, so it would be the 83.4. My volume is in centimeters cubed. And so when I rearrange this, I'm taking away my pressure. Okay, so my unit analysis, to make sure that I've rearranged everything properly, kilopascals cancel out with kilopascals, left with centimeters cubed, which makes sense since I'm solving for a volume here. So my V2 equals 2.9 times 10 to the 2 centimeters cubed. So the reason that I have to put this one into scientific notation is because, remember, I only have 2 sig figs that I'm allowed to use in this question here. So I can't write 290. Question for you guys. Why did I not subtract the amount of water vapor from my P2? So why didn't I take it away from the 101.3? So hopefully you were thinking that we didn't take that away because I've already essentially dried out the gas. So by taking the water pressure away from step 1, I've already dried out my gas, and then I'm going to increase my pressure up into 101.3, assuming that my gas is already dry. If I subtracted 1.1 from that again, then essentially you're telling me you're taking out the water pressure twice, so really you're taking out more water than would have actually evaporated into that system there. Okay, so I want you to try number 5 on your own, and then in the next video I will post the solution to that one so that you can double check your answer.